Welcome back. We will be talking about data cleaning today. So in order to get to these slides, you should be able to go to the introduction to our website, scroll down all the way to data cleaning. And again, we'll be using the HTML slides for this lecture. So before we jump into data cleaning, we're going to be talking a little bit about subsetting data with brackets. So in R, there are a number of ways you can subset data. We've spoken about a few of them, such as select or the $ operator for data frames, but there's kind of a more general way of doing this, and there's a different way of doing this for vectors specifically. So let's say we have a vector X that has 5 elements, 1, 4, 2, and 8, and let's say we want the second element. So here, if we say X single bracket 2, it'll return the number 4. So as we see here, the second element in this vector is 4. Now note that R is 1 indexed. So the first index is 1, 2, 3, 4, 5. Some other systems like Python and things like that are 0 indexed. Don't worry about that. 1 represents the first element. There is no 0th element. And whenever you index things, it has to be a positive integer when you want to grab things out. And we will talk about how to delete things from a vector, and they can be negative in that setting. So I'll show you that on another slide. So there is a dplyr function that will pass in a vector, and you can specify which singular element from that vector you can extract. For here, example is nth. The nth function is that you pass in the vector and tell it what index you want to grab. This is particularly useful. So let's say you group a data set by a patient identifier and you want to grab the third measurement or something like that. There are also wrapper functions of first and last, which are wrapper functions for the nth function. So here, again, we have the exact same vector, and we can subset the data for the 5th element for 5, and we can pass in a number of indices for this subsetting. So here we want the 2nd and 5th element, and again, because we are subsetting, we have to pass in a vector of indices, and here we have to use that C function, the collect function, to make that into a vector. So here we're saying get the numbers 2 and 5, collect them together, and then we're using the bracket notation to subset X on the 2nd and 5th element. You'll note here that the number switched around a little bit. So the 2nd element is now 2, and the 5th element is 10. So that's what is returned, a vector of length 2. Now note, although the dplyr function is really good, it will only allow you to grab a single index. It won't allow you to grab a number of indices. You have to do them in separate nth calls. So here, if we pass in a vector of 2, the 2nd and 5th elements, we can't do that in here. It only can be 1 index that you're grabbing. So again, if you put a negative sign or a minus sign before integers, that indicates you want to remove these indices from the data. So X and then bracket -2 means I want to return every single element of that data set or that vector, but the 2nd element. So if you see here, if we go to the last slide, 1, 2, 4, and 8, the 2nd element is 2. We say X subtracting off the 2nd element, and we get everything back except for that 2nd element. So you have to be careful with the syntax with dropping more than one element. If you want to drop the first 3 elements, 1, 2, and 3, you have to do negative times the whole thing. You do -1, -2, -3, but you have to make sure you're really not, or you're trying not to jumble positive and negative indices. So for example, here, the colon operator we've talked about, which will give a sequence of numbers, 1:3, which will give you the numbers 1, 2, and 3. If we say negative around the entire thing, we could have also collected this together, but we don't have to in this instance. But you need to put parentheses around it to say you get 1, 2, and 3, and then everything becomes negative, so it drops the first 3 elements. Now, I will show you what happens if we do the other way. So here, hopefully you can see that. I'll make it a little bit bigger. So we say X, and we say -1 to 3, thinking, hey, we're trying to drop the first 3 elements. So you'll get an error that says only zeros may be mixed with negative subscripts. So again, you have to be sure that you're not mixing and matching negative and positive subscripts to index a data set, because it won't understand what you're doing. So either you are dropping specific elements or keeping specific elements. You can't be doing both of them simultaneously. So again, we can create logical indicators with vectors or using the standard, comparison operators, greater than or equal to, less than or equal to, not equal to, or the double equal signs that represents equality. So here we have the vector x, and we're saying is x greater than 2. We see 1 and 2. They are both not greater than x. If we say greater than or equal to, this element will be true because 2 is greater than or equal to true. But we get a vector back with the same number of indices, or sorry, same number of elements as the original vector x. So x was length 5, x greater than 2 is length 5, and we get trues and falses from that. We will talk about missing data in a second. So we can also index data sets or subset vectors by logical indices. So we don't just have to say, I want to get rid of element 2, I want to get rid of element 3. We can say, keep the elements or return the elements where this condition is met. So you say x bracket, and then you pass in a logical vector that is the same length as x, and it'll give you the elements of x where that is true. So just like there are logical operators like greater than or equal to, not equal to, and all that kind of things, there are logical operators. So the ampersand is and. So for that to be true, two conditions must be met, or multiple conditions must be met simultaneously, or at least one of the conditions must be met for a true to result. So x greater than 2 and x is less than 5. This will give us logical indicators of all the elements of this, 1, 2, 4, 8, and 10. We see 4 is the only one that is strictly greater than 2 and less than 5, and we can pass in that logical vector and we get the element out. Now, alternatively, we can say x is greater than 5 or x is equal to 2. So again, note these are double equal signs. It is different than an equal signs that is used for assignment or within functions to define a argument. So here, this will return trues and falses, and we get back all the elements that are greater than 5, 8, and 10, as well as those that are equal to 2. So 2 doesn't meet this condition, but it does meet this condition. 8 meets this condition, but not this one. But the OR says if either one of them is true, return true. So the which function converts this vector of trues and falses and gives us the indices that are true. So if you have any NA values in there, it doesn't return those. It only returns where the elements are true. So again, we could have done the same thing we did before in the last slide. X is greater than 5 or x is equal to 2. We could have also used the which function to get those indices and then subset based on that. Sometimes the which function is very helpful because it can tell you the rows of a data set where a condition is met, so you can actually investigate those a little bit more. So data cleaning is a process of investigating your data for inaccuracies or recoding it in a way that makes it more manageable, or finding just problems with your data. So rule number 1 of any good data analysis, it's the most important rule, is to look at your data. Never assume a data set is clean, no matter how much you trust the person who gave it to you. Now we'll talk about some other very useful checking functions. Is.NA will return true if the data is missing, and it will return false otherwise. So if you say is.NAX, it will tell you false if that value is not NA or not a number. It will tell you true if that value is an NA or not a number. Not a number can occur when you divide 0 by 0, for example. So the bang or the exclamation point is a negation. So it turns trues to falses and falses to trues. It doesn't do anything with NAs if they are in that logical vector. So if you have a vector X, and you say is.NAX, and it gives you a value of true for one of those indices, and then you do not is.NA, then that will turn that result into false. So what we're saying here is return true for each element of X if it's not NA. Okay, so is it not missing? Then it will come up true, right? So that's what we're saying here. Is.NA will say true, it is missing. Not NA will return false if you have an NA in there. So pretty much, is this not NA, or is this data real? There is also a function called is.finite that will give you a true if the data is not NA, NaN, or any infinities, negative infinity or positive infinity. So they are Infinity is described with capital I and F. Negative infinity is a negative, capital I and F. Infinities and negative infinities can happen when you divide a positive or negative number by 0, respectively. All is a function that takes in a logical vector and will be true if every single element of it is true. So for example, all is not NA. We'll say, is every single element of X not missing? If that is true, then this will come up true. If any of those elements of X is missing, then this will come up false. Any is kind of a complement to all. So any will become true if any single element of that vector is true. So if we say any is dot NaX, so this will say turn every single element X a true or false, saying, hey, is it NA? And if that comes up true, then this whole argument or this whole function will come up true because it says at least one of them. So any is also a surrogate for as at least one of them true. So complete.cases is also a very useful function. It returns true if every single value of a row of a data set is not missing. So everything has to be in there. So this is a very stringent condition. So even if you had a column that was just like, a comment column and had no column or comment in there and it was missing, if you say the complete.cases, the rows that have at least even just missing values on the comments will still come up false. So again, it'll be false if missing at least one value, even if it's not an important variable. So there's a tidyr function called drop NA that will drop rows with any missing data. You can use these functions, but be very, very sure you've explored your data and make sure that you are dropping the rows that you want. So dealing with missing data. So again, one of the most important aspects of cleaning values is missing data. NA is a general missing value. Unlike Stata or SAS, there are no varying levels of missingness. There's not dot A, dot B, dot C like there is in Stata. There is no, differential coding for those. You would actually code them into a factor yourself. NaN, again, stands for not a number. It happens when you do 0 divided by 0. Infinity and negative infinity happens when you take a positive or negative number and divide by 0, respectively. So again, we've already talked about is that NA will return true if that value is NA or NaN. Is that NaN is a little bit more strict. It says, is it not a number? Is that infinite will come up true if it finds infinity or negative infinity. Is that finite returns false for all missing data and true for non-missing. So if we look at this, so see inf, negative inf, and you see that the colors change because they're special in R. Okay, is that finite? So for infinity, negative infinity, NA and NaN, this will come up false for all of those values and true for anything else. This works on logicals or numerics or integers. So one important aspect of bracket subsetting is that when you do logical operations on NA values, it almost always will return NA unless there is a condition that sets it to be true or false. So I'll show you what I mean by that in a second. So let's say X is this vector that we've presented here. And let's say we say X is greater than 2. Well, we know 0 is not greater than 2, so that comes up false. Well, there's a missing value there. That value could be negative 10. That value could be 100. That value could be greater than 2. We don't know because simultaneously it could be two different things. We don't know what it is. We cannot make any assessment in this logical condition as to whether this is greater than 2 or not. So it's going to return NA. Now, what if we wanted to get a logical vector back that said, I want something, is it greater than 2 and X is not missing? Well, I could try to say X is not equal to, this is the not equal to operator, right? But you shouldn't do X is not equal to NA. And again, let's think about why that is the case. This value is an unknown value. So how can I say something is not equal to an unknown value? It could be equal to it. I don't know. So that is the reason why everything in this vector returns .na. That's why those functions is.na, is.nan, is.finite, and all other things like that exist. So here we're saying, is x greater than 2 and it's not missing, okay? So if we go back and contrast between x is greater than 2, we have an NA here, versus this, we have a false here. So the AND operator, again, so if you have a true and a false, it's going to come back false. If you have a false and anything, it's going to come back false. The only way this is true is if both conditions are met. So x has to be greater than 2 and it cannot be missing, okay? So an NA will come back missing here, but because anything and a false thing is always going to be false. It doesn't matter if this answer was true or this answer was false. Once you do an and with that, we know that the answer has to be false. Okay? So usually when you're trying to do testing for some of these things, you still want to note things about missing data. When we talk about filtering, it pretty much keeps rows that are true and removes any values that come back missing. So it's kind of like which, right? So when we filter rows of a data set based on a logical condition based on one of those variables, pretty much it'll say, I will return all the rows for that's true. If those rows come back missing, it's going to be removed. If you want to keep them, you have to make sure you put a condition like this condition, or this value is missing. So, you can do complex logical operations here. So for example, we can say x is equal to 0 or x is equal to 2. So again, the first element of this data set was 0. The third element was 2. So we get trues for that. The other ones aren't 0 or 2. But again, we see NA because that value could be 0 or it could be 2. We don't know. This operation is similar to what we've done before. Is x equal to 2 or is it equal to 0? And is it not missing? Again, this will turn that element to false because this is that NA for that value will come up true. The exclamation point negates that. And so that becomes false. And so again, false and any other logical true or false, it doesn't matter, will always come up false. So here I'm doing the exact same thing, exact same data set, except that now I'm turning into a tibble and we're using the tibble function to create that. And we're using the piping operations we've shown before. And so the filter command, again, filters the rows based on some logical condition. So we say df pipe that data set into filter. And we're going to filter where values of x is greater than 2. And again, if we go back to the original data set, we see that these elements 3 and 4 are the only ones that are greater than 2. Okay, so there are other helper functions like between. So instead of doing greater than -1 and less than or equal to 3, you have to look at some of the arguments for between, and we'll look up that in a minute for if it's strict or non-strict inequality. So you see the fact that 3 exists here indicates that it's at least inclusive. To say like if it's between -1 and 3, it can still be 3 or -1. So this is one condition, and we're saying keep the rows where x is between -1 and 3, or it's missing. It's a missing value. So again, if we didn't put that in here, this row would be gone. So if we go back and I say between left and right, you see here that yes, it is indeed a shortcut for inclusivity. It's greater than or equal to x and less than or equal to, or x is greater than or equal to the first value and less than or equal to the right value. Okay. If you want to do anything without strict inequality or with strict inequalities, you can just do that yourself with logical comparative operators greater than equal to. So there is a function called percent in percent. Okay, percent in percent takes a left-hand side and a lookup table on the right-hand side. It says, are x values percent in percent is, can you find values of x that are in this vector? And it'll come up true if things in x are in the thing on the right-hand side. So we know the first and third element are 0 and 2. So yes, it says I found that true. I found that true. And you can technically also put NA in there, but I would not recommend it. This makes a lot more sense to most R programmers. This is not technically wrong, but it's kind of bad form, and it can maybe get you in a little bit of trouble because, again, we showed you that example where it's like X is not equal to NA. So you want to make sure you know how to handle missing data. And what you should be doing is X in these set of values? Is it 0 or 2? So let's say it was 0, 0, 0, 2, 2, 2 NA. All these would be true because all of them are within 0 or are equal to 0 or 2. So this is a nice way of doing things instead of having, say, X equals 0, X equals 2, X equals 3, X equals 4, right? Or. So this alleviates having to do X equals 0 or X equals 2 or X equals 3 over and over again. But this is a better way of kind of describing what you're trying to do and that you're thinking about the missing data. So is X 0 or 2, or is it NA? And we see, again, that'll give us trues and falses. So again, when you're working with missing values, that will also result in NAs because we don't know what this value was before. If we say X plus 2, it's not going to matter. That number could be a million or negative 5,000. I don't know what it is before. I don't know what it is plus 2. Similarly with multiplication. So let's stop here and let's move on to the first part of the lab where we do a little bit of data subsetting and data cleaning and missing values. Okay, I'm going to pause here and then I'm going to move on. So you should take a pause, do the lab, and then come back. So tables and tabulations. So again, we've talked about unique in a previous lecture. Unique gives you the unique values of a variable, including the NAs. Table will give you a one-way table of X. There is an argument in table that says use NA. You can put that as always. You can say if any, or you can use the default, which removes the NAs. So if you say table X and there are missing values in there, it's automatically going to drop those unless you change the use NA argument. So table, similarly with two-way cross tabulation of X and Y, it is a useful thing because sometimes stratifying the data by two variables can allow you to see patterns of missingness or issues like that. So again, we've talked about the count function. We could pipe a data frame. So again, DF is just a generic data frame. It's not an actual data set we've got loaded in memory. We're piping that into count, and we can count X, Y, Z, count a whole bunch of variables, do three-way, four-way, five-way frequency tables, but it's going to do all combinations of X and Y and give you the frequency. Alternatively, if you think in a better mindset of grouping data and then counting them up, there is a function called tally, which we've hopefully touched on in the past, which groups the data, and then when you tally it up, it'll do the same thing as above. So again, like I showed you here before, or I said before, unique will keep the missing values in there. If we do table, we have a frequency table. There's only one of each kind, but you should note that NA is gone. Also, if we table X and say use NA equals if any, because there is a NA value in there, we will have an NA in there. Now, I'm sorry, but this is a little bit cut off, but when you use count, the missing values are also kept. Oops. So let's say we have another vector that's just 0, 1, 2, 3, 2, 3, 2, 3, 3, and then we table that together. We would say use NA equals if any, and then if there were NAs, we know there are not, then it would have a column for NAs. But because there are none, there is no column for NAs. If we said always, it would have an NA column here with a 0 in there. Some people really like that because you can force a 0 row when you're trying to do frequency tables for reports and things like that. So again, here we're making a tibble on the fly, running count X. Again, we get a frequency table very similar to table, but it is a tibble now, so all your dplyr functions will work on it. So like I said before, if we change that output to use NA equals always, we see a 0 row for missing values. So tables with factors. So sometimes it doesn't matter if the a vector you give in there, you want a row for every single level of that factor. So here we're making a factor on the fly, 0, 1, 2, 3, and so forth, but we say levels are 1 to 4. Now note, because 0 is not in these levels, it's going to be converted to NA. That's not a great thing going on. But also we see we put level 4 in there, but guess what? There is no 4 in this data set. So if we do tab, set it equal to the table function, what it will do, again, because 0 turned into NA, it goes away. But because we have 4 different levels, even though there's no elements of that data set that are in level 4, it still shows a 0 there. Now we can also subset the data where the elements are greater than 0, aka there's more than one record of that. And again, count will do what you want it to do, but it will give you a warning, say, hey, you should probably make the factor with explicit NAs so you actually have a category of missing and things like that. So again, similarly with a one-way frequency table, if you put in a vector X and a vector Y in here and you assign the output to tab, you'll get a two-way frequency table, and you say use n equals always. They'll have a vector of a row of zeros for each one because we have no missing data. Now, why are we talking about table if we're going to use count all the time? Because when we do statistical tests, it is important how you can construct your tables, because chi-square test, Fisher's exact test, things like that actually take in a table object to do those. And it's important because if you say use n equals always, what a statistical test of like Fisher's exact test or chi-square test says is the distribution of values the same across the rows and the columns, right? Does it have any dependence on, are the columns and rows independent? That's essentially what they're testing. And one of the issues with it is you are artificially inflating this table with a bunch of zeros that aren't real. Now that can be problematic. That can be less problematic if they're all zeros, but it is problematic if you are having missing data in there, because you aren't just testing the distribution of the data, you're also testing the distribution of the missingness. So just be aware explicitly what you're testing when you're doing testing in the statistics lecture, and this use NA argument can be really influential on that. So again, we're going to do the same exact thing we had before, except we have to turn it into a tibble. So count and all those things, they work on data frames or tibbles. They have to have rows and columns. But again, similarly to what we did before, making this frequency table, we get a more condensed version here that is a two-way frequency count. So there are functions in R that allow you to get the margins of a table. So if we go back to here, tab is this. And if we say margin.tab, we have to tell it what margin we want. Margin.tab will do the marginal sums. So we either really pass it the numbers 1 or 2. So again, in R, the way R thinks, rows is the first dimension. The second dimension is columns. So here we're saying I would like the margins over the columns. Okay, so if we look at this, we see 1 here, 2 here, 4 here, right? If we had taken it across the rows, we 1, 1, 4, 4, which we'll show you in another slide. But here, the margin table and putting the number 2 in there, which is the margin, what we're doing, we're saying we're doing it over columns. Similarly, instead of margin.table, there's prop.table, which is a table of proportions. So if the margin is not set, it divides by the overall sample size, the overall total. So these will all add up to 1 if you don't give it a margin. Now, alternatively, here we're saying 1 instead of 2, like in the last slide, and now we're doing row margins. So you'll see that every single row now sums to 1, and we added and multiplied it by 100, so 100%. So here saying take the table, do the proportions or the row percentages, if you will, and then multiply it by 100. So one way you can do that in dplyr, again, you can count. You can do count, which will give you the two-way frequency table, similarly to what we had on the previous slide. But now if we want to turn these into percentages, it could be row or column percentages, but it just depends on how you group the data. So we had that original data set or that original counting that gives us these numbers, but now we want to say, hey, I want a percentage of that. And so the way you would do that is you would group it by X. So you see X here is these two elements both have the number 2 in there. So we're going to perform operations with these groups independently. And it's going to say, we're going to create a new column. So we're going to mutate, and we're going to say, take this n, divide by the sum of n. So divide by the total number in there. So here we had a frequency of 2, a frequency of 2. And again, we grouped it by this element. So it said, take these two, split them off, and divide this number by 4, the total, this number by the total, and that total is 4. So they're each a half. Everything else is 1 because there are no other groups of X that have the same value as any other ones other than 2. Similarly, you could have done it with Y. So there is a function package called scales, which is very helpful. And we are doing the exact same thing we were doing from before, except of doing this where we say n divided by sum of n and we get a proportion. There is a function called percent, which I think is pretty handy. That will give you percentages. It'll make it into a character. You can tell it the number of digits you want and all that. Okay, so this whole slide is just telling you there's a percent function in scales, as well as a whole number of other scales and helper functions that are useful. So we're going to pause here and go to the second part of the lab. So I would say go to the website and download the lab. So again, if you go here, you should be able to go to the website and there should be a lab on data cleaning. And you should be able to download that and open it up. Okay, so moving on. So here we're going to talk about some salary data from the Baltimore City government from quite a few years ago, 2014. So this should be a link to the employee salaries from that year, which you could download. So we could read these in a number of ways. So again, this is included with the JHUR package. You could have read the CSV straight away from one of these links. But what we're doing is creating a new data set called SAL with a capital S, and we're renaming the first column to be name with a capital N, even though it came in as a lowercase. So we're just renaming the data. So again, all and any are going to be used here that check to see whether a condition is all true or any of them are true. So here we're saying Sal $name. So again, we are grabbing the name column from the Sal data set. We could have done this in a dplyr framework, but this is kind of simple enough. So we're saying grab that vector, put it in the is.na function. So it'll turn any NAs to true. And it says, are any of them true? And the answer is false, which means there are no missing names in this data set. Now, recoding variables. So there is a function called recode in dplyr, which is pretty helpful, and we'll also be talking about the if-else function. So again, we're going to reassign the data. So we're going to overwrite it. So we want this to stick. So we're saying the data set, we're going to pipe it in. And remember, every dplyr function, the first argument is the data, and that's what the pipe does. It takes that thing and puts it in the first argument. And now we can say we're going to mutate this data set, and we're going to replace gender with a recoded version of gender that if you had M in the data set in gender before, it's going to be now male. If it was lowercase m, it'll be male. If it was uppercase M, so you can repeat these, it was going to be male again. So you could put these in quotes. You don't necessarily have to, but it's saying old is equal to what, or what do you want to replace the old with? This is the old thing. This is the replacement. Alternatively, you could have done data and piped it in and said an if-else statement. So this is a way of testing something is if true. So we're saying, is gender in capital M male, capital M, or lowercase m? If any of those conditions are met, this is the true thing so if that is true, the next thing is returned. Otherwise, we're going to keep it as is. So if-else says logical condition. If that thing is true, what do you want me to replace it with? Or what do you want me to output? Otherwise, we're going to keep it as is. So after if we want to see all the different versions that people have encoded gender in this data set, we can see that here, for example, male, MA, different, spellings and things like that. We could use those functions to lower or to upper to make everything uppercase or lowercase, or we could do a lot of recoding. So I don't know if that's more complicated, but so string functions. So we will be touching very lightly on this whole thing called regular expressions. R can do so much more than just exact matches for a whole string. So Perl and other languages uses this kind of sub-language, if you will, called regular expressions. So ways to search for specific strings can be very complicated or somewhat simple. It's highly useful. Think of Control F or find on like all revved up and with so many more capabilities like the Cadillac of find. So we are not going to teach you regular expressions. Some of them can be very, very, very complicated. So I would suggest taking a look at this reference here. You can use them to match a number of strings in one statement. Period matches any single character. Star means repeat that character as many times, even 0 more times as the last character. Question mark makes the last thing optional. The caret matches the start of a vector. So caret A means starts with A. Dollar sign means the end of a vector or an end of a character string, really. So B dollar sign means it ends with B. So the string R package makes string manipulation more intuitive, has standard format for most functions. The first argument is a string, like the first argument in data frame is dplyr. So string R, every str function, and that's what they're all prefixed with, str replace all things like that. Every single one of those functions, the first argument is the string, is the vector you're trying to do manipulations on or detection on or things like that. So we might show you things like grep or gsub or grep is also referred to as that. I would say it's used in a lot of forums there. Andrew and I use it pretty consistently, but that's not what we're going to teach you because the string R package gives you a unified framework. It's also in the tidyverse, so it kind of fits with everything else. So we can look at different modifiers. So if you go to the help file for modifiers, which I'll jump to in a minute, there should be a number of explanations there. So some of the modifiers are fixed. So match everything exactly. Regx, which stands for regular expressions. So that's the default. So ignore underscores case is an option to not have to use like you lower or to lower. So like, for example, in that previous case, we were trying to find MA and it might have been uppercase and lowercase, lowercase and uppercase. If you're trying to find something and say ignore case equals true, then it will not look, it will not treat those any differently. So if I go to modifiers in my RStudio, it'll say compared literal bytes to the string. There are other ones, collation rules, which we're not going to talk about. But more or less, you put these in the string R functions to change the behavior if you want. So sometimes you want to find something, and let's say you want to find a dollar sign, for example. Dollar sign, well, like we just talked about, is a special character. Dollar sign means the end of a string. But if you're like, no, I actually just want to really find dollar signs. I don't want to find the end of the string. So you would wrap that dollar sign in fixed. So you'd say like fixed dollar sign. Or let's say I'm looking for the letters MA, right? And I say ignore case equals true, right? That would be an example. I'm looking for MA anywhere, but like the word female, str fine, detect. So I have to load up the string R package in a second. I'm going to pass in the vector female, male, male. Missed a quote here. And again, string R is included with the tidyverse. You can load all that up at once. Let's try this one more time. So it says true on all of these because it found the letter M and the letter A. We didn't say the beginning of a line, anything like that. But if I say ignore, whoops. If I don't put that ignore case in there, we see that it's true for these two, but not this, because there's a capital M and a lowercase a. So that is one reason, one thing where the ignore case is very useful. So again, we will talk about a lot of these in like short detail. String manipulation, string cleaning is hands down one of the hardest things to do, especially if you have messy data. Pretty much free text fields are the bane of my existence sometimes, but we'll try to give you some tools to help you with that. So there's str sub. So str sub will take a substring, and you say the start position to the end position. So let's say I want the first 3 characters of everything. I would say substring, give it a vector, and I would say 1 to 3. And that'll give me the first 3 characters of any given string that we have in there. So let's say we have these 3 character vector of length 3. So X is I really like writing R code programs. So str split will take in the string, but it'll split based on a pattern. So in this case, I just want to split the string based on a space. So this returns what we're calling a list. So a list is something that's highly complex, but it's also like just a catch-all container for kind of anything. So we've talked about data frames. They have the same number of rows for every single element of that data set. But again, every single column could have a different data type. So age, you could have indicators of, did you get treatment or not, things like that. A list is a lot more flexible in that it just gives you a number of elements, and they could have different lengths, they could be of different types, things like that. So here's an example, one of the few examples we'll talk about in this class where a list is returned. And that's what this weird output kind of looks like with these double brackets. So this is a list with 1, 2, 3 elements, and the number of elements in the first element of the list is 2. The number of elements in the third element of the list is 3. The number of elements in the second element of the list is 2. So again, if you see anything output like this, it is generally a list, and we will talk about them very briefly when we talk about statistics a little bit later. So again, we talked about special characters. The period is special. It means I'm going to match on any single character. So if we try to do str_split on I period like period strings period, and we say, I want you to split on the period, it does not do what we want. It gives nothing back because it's split on every single character. If we say str_split, pass in the same string, but now we say this is fixed. I don't want you to treat it any fancy. I don't want you to treat it as one of your fancy regular expressions. I just want you to find the actual period. What you see here is it does in fact split that single string into 3 different elements, but again, it returns a list. That's why you have these weird brackets. So extracting elements from lists is a little bit different than vectors. So instead of singular brackets, for lists, if you want to grab the thing inside the list and extract that actual element, you have to use double brackets, okay? So double brackets means I want the second element of that list, and I want to grab exactly that thing out. So here, going back, Y is these 3 elements, and I'm going to extract the like writing element out of all of them. So also, we will not talk about these in more detail, but there are a set of functions called apply functions that are really useful for lists. We do not teach per_r, which is one of the tidyverse packages out there. So if you're interested in string list manipulation, if you have to end up doing that, I would highly suggest taking a look at that package. We will also show you how to split columns of a data set based on some identifier into multiple columns. So let's say you had like ID_site_visit. We will be able to show you how to split those things into multiple columns without having to do any of these string manipulations. But generally, if you're doing any data cleaning, string manipulation will be happening. So these apply functions take in a list and they perform a function on that. And sapply tries to simplify the output as best you can. So sapply takes in this list of 3 elements, and what we're using is dplyr, the first command. The first command extracts the very first element of that vector. So here, remember, it's I really like writing code. If we say first, this is the first element, this is the first element, this is the first element. So it loops through each one of them and gives us the first element. Now, alternatively, we could use the nth vector, and we say, hey, I want you to grab the second element. If we go back, this is the second element, this is the second element, this is the second element. So again, we spoke about this very briefly before. This is, with the rename all and things like that, where you pass in a list, a function, and then any additional arguments to that function. So we could have said n equals 2, and that's essentially what we're doing here. Grab the second element. Lastly, we could say, instead of first, we could use last, where it'll grab the very last element of any one of them. So it doesn't matter that this has 2 elements, this is 2, this is 2, or 3. Doesn't matter if this is 2, 2, and 3. It says this is the last, this is the last, that is the last. And I'm really writing programs. So again, an alternative way of doing these things, it's a little bit more constrained, but in many instances, this is what you want to do. You have a column of a data set, and you want to split the data set up using some separators. So again, we're going to make a tibble because dplyr, and this is now tidyr. This is a tidyr function called separate. So if you have the tidyverse included. If we go back here, I'm just going to show you again. I'm just going to load up the tidyverse package, tidyverse. We will see what packages are loaded. And we see tidyr, yes, is part of the tidyverse. So if you load tidyverse, then you're fine. The separate function is available to you. So the way you do this is you, again, pipe in a data set, or you put the data set as the very first argument. And then you say, what is the column that I want to separate? So in this case, I want to separate the column X. And what do you want to separate it into? So into, we'll pass in a character vector and say, what do you want to call the new columns that come out? So, and it will guess what separator you're trying to use. It'll actually use a whole different number of separators. Anything that's not essentially an alphabetical number, or an alphabetical value, or a number. So anything that's not alphanumeric, like the letter A, B, 2, 5, anything that's not that, like periods or dashes or slashes and things like that, it'll say you want to split on this. So what we're doing is saying, I want to create 3 columns from this data set and split it how you'll guess. And this guess is by spaces as well. And so here we get the first element, I like R, really writing code. And then you don't have a third element for this one. You don't have a third element for this one. You have programs. So that's why these are missing, and it gives you a warning and say, hey, these missing pieces are filled with NA for rows 1 and 2. So if we don't give it enough things into that into argument, it'll actually cut them off. Just say like, hey, I want the first and second thing. And now we see that word programs is now removed, and we see a different warning and said, I expected only 2 pieces. We had additional pieces and I discarded them. So there are there are arguments, additional arguments in the separate function. And one of them is called extra, which says like, hey, so in this setting, we say there was extra stuff. Like, what's going on? Like, you just got rid of them. And if you do that here, you just say like, hey, if you find anything extra, just merge it with the very last thing in there. So here we change things up a bit. It says, I really like period underscore writing R code, but not R programs. So it won't separate on the period unless you tell it explicitly to do that, but it's separated on the space and the underscore. It got rid of both of these things when it said, oh, I apologize. So it will split on the period as well. So it's split on all these things. It gives you it gives you writing, and then it's split on the space. And then it said, hey, I already got the 3 things. And you said anytime, you only said I should have 3 things out, and anything else you just lump on the back end. And that's why it pasted all these things together. So we could be explicit and say, what is the separator that we are using? So here, again, everything's the same up here. We're merging everything, but now we've given it a specific separator that is a space. So before, it separated on a whole bunch of things that it tried to guess. Here we're saying, no, I only want you to split on spaces. That's why if we contrast this row right here with this up here, we see we have a period and the underscore there because those weren't removed because it didn't guess those as separators. Okay, so find function. Most of the time you want to find some sort of pattern or subset the data based on something, and these functions are for you. So str detect, str subset, str replace, str replace all. Search for matches to an argument pattern within each element of the character vector. So you give it a character vector, like one of the columns of your data set, and it returns something. So str detect is one that's super, super useful with filter. So it returns a true if that pattern is found and false otherwise. str subset returns only the strings in which the pattern was detected. So it's very much like a convenience wrapper around X, and if you subset on the true values. So let's say you had that MA example from before. So let's go back to here. So let's say we did str subset. So we've talked about str detect. We had ignore case. Sorry about that. So it says, hey, I want you to grab any of the things from here where you find the letters MA, right? But it's got to, we didn't put ignore case. So it says, this has MA, this has MA, this is an MA, but guess what? That's an uppercase, and we are not going to subset those out. Okay? So that's what str subset does. Str detect gives you trues and falses. Str subset actually only returns the subset where it's true. It's kind of like a logical vector and which on that, but it's subsetting a character. Str extract. So str extract is a little bit different. It returns only the string which the patterns were detected, but only the pattern. So this isn't as useful for fixed things like this. So it says like, hey, I want to extract MA from all these things, right? So it says, oh, found an MA, didn't find anything. Now, this can get a little bit different when you're doing things that aren't just fixed expressions. You can do star, dot star, which means anything repeated as many times as you want, and look for the letters MA. So we get FEMA and MA here for everything up to MA and then stop. So that extracted the string. So sometimes that is useful in what you want to do as well. So str replace replaces a pattern with a replacement the first time it finds it. So you want to replace every letter of A with the letter B. It'll look through all of them, change all the A's to B's. Str replace all will find every single instance of it and do the replacement. So like I talked about before, so one of the previous mayors of Baltimore was Stephanie Rawlings Blake. So let's use str detect to see if we can find the name Rawlings. And again, we didn't use ignore case or anything like that. So by default, it's going to say you have to be exactly capital R AWLINGS. And we're using on this column of the data set. Again, we're using the $ notation to get that out. And we're just using head to grab the first 6 elements. So because again, like a str detect gives a logical vector, we can do which on that, and it'll tells us the row indices in which that element is true. So the 10256, 10257, 10258, those rows of the SAL data set actually found the word Rawlings in the name. So str extract, one of the big differences is, right, it'll return NA if it doesn't find the string. So if we say SS is equal to str extract, we're trying to find the word Rawlings. We see NA for a whole bunch of times. And if we subset that data based on bracket notation, which we talked about at the beginning of this lecture, you'll see that it extracted Rawling over and over again. So again, str extract is not so useful if you're finding an exact string. It's trying to, if you're doing a more regular expression thing, str extract is pretty useful for that. So str subset, again, different than str detect, will return the full elements where that thing is found. So here we say str subset, sal name, Rawlings. We didn't have to do anything else. Again, str extract, for example, gave if let's say there was 1,000 rows of the data set, there'd be 1,000 elements in this thing. This, on the other hand, returns only the records where it is true, but it returns the entire string as opposed to str extract, which returns only the thing you were searching for. Okay? So str detect, I would say if you're going to learn anything, str replace all and str detect are the two things that are take-home messages that you definitely should know, because the combination of str detect and filter is very, very, very powerful. So again, we're taking this data set, we're piping it into filter. We want to grab the rows where this is true, because str detect gives us trues and falses. We're using the name column. We don't have to use any of these $ because we're within the dplyr framework. So it says, fine, give me all the rows where you find Rawlings in the name, and this returns an entire table with these 3 records where it found the word Rawlings. So here are some examples using regular expressions. So we're going to be using str subset to show you the things that it extracts, the full elements. So let's look for the name Payne at the beginning with a Y in it, and it has to be a capital P. Let's look for Leonard. And then there has to be something and then an S, Spence, and then the capital C. So this first one, we say carrot, say at the very, very, very beginning of the string, it has to have the word Payne. So if it was like space capital P, it wouldn't work because it's not at the very beginning of that string. So we see these 3 elements from that data set that have the word Payne, that's their last name, for those records of city employees. So here we're saying Leonard Fine, you can have anything you want, like one time optional. It could have nothing in there, but it could be anything you want and then an S. So in these two instances, it's a space, but it could be a period, it could be a slash, it could be the letter E, it doesn't matter. So here we are subsetting data where we find the word Spence. It can happen anywhere. It could happen in the middle of a name. Anything, then the letter C, and then anything. So here is an example we found. Spencer, a comma. So these three elements are kind of encapsulated in this dot star. So these are, anything repeated as many times as you need be. So these things, it found Spence. The R and the comma. It found Spence, a bunch of stuff, and it found the capital letter C, right? Same thing with here. Here, it found the word Spence, had an R, a comma, the Michael, a whole thing space, and the letter C. So those things matched what we were asking. So str extract all as opposed to str extract extracts all the match strings. So str extract is very useful because you can extract a specific thing, like the first thing of a data set or of a character vector that you want. So if we say str underscore extract, we give it the agency ID, and then the way you have to say digits, like I want to look for a number, it's actually this slash backslash D, which stands for digit, and it extracts the first digit that it finds in any individual element of this vector. But if you say str extract all, it'll give you all the digits that it's returned. And note here from this weird notation, it is also a list. So str underscore replace, again, we'll take in a character string or a character vector, and it'll replace some pattern with a replacement. So in this case, every time it finds a lowercase a, the first one it finds is going to return with replace it with a J, because str replace itself just does the first element. So this was Aaron, and now this one was replaced with a J, but you note that this one was not. Now, if you do str underscore replace underscore all, put in that same vector, and you say A to J, we see this A in Aaron was replaced, this A in Patricia was replaced, this A in Patricia was replaced as well, and so on and so forth. Every instance it finds of a lowercase a, it's going to return a J. So, so replacing data is kind of very important, because sometimes you have data come in that has elements in there you want to get rid of. So let's look at the annual salary. We would want to look at an actual distribution or a histogram or something of the annual salary, but we see the class of it as a character. If we look at the first four elements, we see it has dollar signs actually in it. So it's like, is R smart enough to get rid of those dollar signs for us? Yes and no. No, because if you try to convert that character vector to a numeric vector, you have to use as.numeric. But guess what? It says, hey, I found those dollar signs. I don't know what you want me to do with them. And so it says, I'm going to return those as missing. Here, what we're doing is we're going to do a mutation where we take the annual salary, replace it with the output. If we took the annual salary vector, we say fixed. Every time you see a dollar sign, replace it with nothing, aka take them out. And we had to use fixed here because, again, dollar sign is a special character. If we just said dollar sign, it would try to replace the end of every single element in there with nothing, and that's not what we want to do. So we need this fixed modifier in there, and then we can say, hey, as.numeric annual salary, we're all good, and then we can arrange the data, for example, in decreasing order by annual salary. So the person with the highest paid job is at the top. We couldn't have done that before because it was a character vector. It wouldn't have sorted correctly. Okay. There is also a function called parse underscore numeric from readr, which is, parse number. I apologize. It is a magical function. What it tries to do is it tries to do all the smart things that you possibly can think of. So if I take away everything here, if I say $1 million at 1.456, and then I said, I don't know if spaces, I don't think it likes spaces. Say parse number. It actually does do the guessing correctly. It says hey, let's take this. Let's make this one not as big. Let's make this 1.45. Let's make it 1,000. Okay, just so we can see it. So it does some smart parsing, but look, it doesn't do maybe exactly what you think it does. 1,000, great. 1.45, great. This is a little bit of a funky one. It thinks you're doing 12 and then a bunch of zeros. So sometimes it does what you want. Sometimes spaces and things like that can mess it up, but it's trying to do its best you can. In something like this data set we're talking about in the lecture, we know that the data is well formatted, but it's still got dollar signs in it. So we can be reasonably assured that the parse number should probably work there. If we're talking about other things or free text fields in there, it is kind of the Wild West. So we talked about separating strings. Now let's talk about putting them together. So two functions that I think are very, very important are paste and paste zero. So paste is a general function that can paste two vectors together. In this case, I'm going to say visit and the numbers 1 to 5. Again, the colon operator makes a string of 1, 2, 3, 4, 5, and I can tell it which separator to use. By default, paste uses spaces. Okay. Paste zero, on the other hand, does the exact same thing. You don't have to say the separator. The separator by default is nothing. So it just slams these strings together with no separator, which is totally fine, which is what you want to do. And you can also put sep equals underscore here and get the exact same thing out from up here. But paste is nice because by default, it gives you spaces. Paste zero by default gives you nothing. Sometimes you want one or the other, but for the most part, I tend to use paste zero a lot. But I want to note the difference between sep and collapse. So sep means I'm taking this, I'm putting this with this. These are two separate vectors I'm pasting together, and I'm separating by underscores, and we get this. Now here, I'm saying paste this vector with this vector. I want it separated by underscores, and I want you to collapse the data by single quote. Now, this, you see these multiple quotes in there. 1, 2, 3, 4, 5 elements. This has one big element. That's all this is. So when we say collapse, it says paste these things together and then paste all of that together with another separator, right? So separator says between these two things, I want underscores, but between each element of these, it's like pasting this entire vector together with spaces between them. So here's an example of putting 3 different vectors. 2 is going to be, we go to the store, and I say the separator is day with a space after it. So it says today is going to be the day space we go to the store. So there are different ways you can use separators and collapsing to manipulate strings into strings you need. Now, just like I talked about string split and that kind of stuff in string R, and I just talked about paste in R, the tidy way of doing that, the tidyverse way of doing that, as the opposite of separate is to unite. So here, what you do, instead of saying, so here are 3 example columns, ID, visit, and things like that. So it's just 2 columns. And so we say data set, and we're going to pipe it into unite. So again, the first element, data set. And we're going to tell it, what is the column you're trying to create? And this column, I'm going to call it unique underscore ID. And then you give it all the columns you want to unite together. So in this case, ID and visit. And then you say, what is the separator you want to separate them with? So in this case, it would have been 1, 2, 3, 4, 5, 1, 2, 3 over and over again. And now it took that ID from this data frame, it took the visit from that data frame, and it pasted them together with an underscore. Now here is the exact same code. Pretty much at the end of the day, it's very similar to paste. You just say, this is the column I want to create. These are the columns I want to create it with. And if you don't set remove equals false, if we look at here, by default, what it's going to do is say, hey, you wanted to paste these together. I assume you don't want them anymore. That's totally my assumption, and it's usually pretty good. But sometimes you're like, hey, I want those columns still. So there's an argument in unite, and there's an argument also in separate called remove. And if you say that equals false, all the columns that you had before that you pasted together or separated will still be there. Now, if you had other columns in this data set, they still will be there. Anything not touched by this will still be there. But for here, the ID and visit were actually dropped because by default, remove equals true. If you set that to false, everything is still in there, and we've also created this new column. So I want to depict very briefly how collapse works. If I say paste So remember, paste by default separates things by spaces. But if I just say paste 1, 2, 3, 4, 5, nothing happens because paste took multiple different elements, different vectors, and paste them together. This is just one vector. It happens to have 5 elements, but it's still just one vector. So by default, the separator doesn't do anything if you just pass in one vector. But what it does is if you pass in one vector and say collapse is space, then that applies to this overall vector and makes it one big element. So some other useful functions out there, 2 upper, 2 lower. It makes all the characters in something uppercase or lowercase. str trim, excuse me, from the string_r package, or the trim ws function in the base and base r will trim all the white space on the left and the right hand side. nchar gives the number of characters in a string. So again, it will not tell you the elements of a character vector, but it'll actually tell you in each element what is the number of characters in that string. So sort, we'll talk about sort reorders the data. Characters work, but a lot of times it does not sort the data in the way you think. Rank gives the rank of the data. Ties are split. Order gives the indices if subset of the data sorted. For example, you say sort 1, 2, and 10. They're characters, and it says 1, 10, and 2. You're like, what's going on here? I don't know why that's happening. It's like because it sees 1, it sees the first element, the first place of this is 1, and then 2. That's how it sorts it. It simply sorts the data. Order is a little bit different. So order says these are the indices if you subset that data, if you subset this vector right here, that would reorder the data set. It's not used as commonly. I would say you never do this on a data set. You would always use a range. So here we are creating 10 random numbers. So our norm is just a random number generator from a normal distribution. And we're just setting the first 2 elements to be exactly the same so we can create a tie. And then just to show you how ranking works. So if we rank X, rank this vector, this element is the first element. It's the highest rank. These 2 are tied for second, so they actually don't get a round number. So they're tied for second and third, so that's why they get the value 2.5. If 4 of them were tied, it would split the ranks evenly from second to 6th, I believe. And then this is the 4th element, 5th element, 7th rank, 8th rank, 9th rank, and so forth. Okay, we're going to pause here and go to lab part 3 of the website, and then we should be able to move on. So that should be data cleaning actually in a nutshell. So there are some extra slides within this lecture about how to compare certain things from string_r to base_r. We are not going to cover them because they can be quite confusing. But if you want to explore this and you have code from collaborators or things like that, and you're saying like they use all these base_r things and I want to learn how to do it in string_r, this could be somewhat helpful. Also, we go a little bit more into lapply and other apply functions later in this lecture. But pretty much this should give you a good tool set for how to manipulate strings. I will still say that manipulating strings is very hard. Regular expressions, I know, is a whole language on top of R, but it is very powerful. So learning at least some of the basics can be very useful for your work. Okay, so let's finish up the lab and we'll move on to the next lecture.